Hello and welcome to today's revision session looking at the forces topic for GCSE Combined Science Physics, and in this particular revision session we're going to focus on the interactions of the forces. So that includes scalars and vectors, contact and non-contact forces, gravity, work done and energy transfer, and forces and elasticity, which are all topics found on paper 2 of GCSE Combined Science Physics. So the first topic we're going to look at are scalars and vectors. Now scalars are quantities which only have a magnitude or a size associated with them. These can include mass, length, temperature, energy, time. Now all these quantities do have a magnitude, but they do not have a direction to act in, they just exist. Now vectors are quantities which have a magnitude and a direction associated with them. So these can include weight, momentum, acceleration, force and velocity. Now all these quantities have a magnitude and a direction they specially act in. So to clarify, scalars are quantities which only have a magnitude associated with them. Vectors are quantities which have a magnitude and a direction associated with them. But we've got to treat these concepts differently, both conceptually and mathematically. But some quantities have a scalar and a vector counterpart. Now in these examples, the vector is the scalar with the direction added. So for example, speed is the scalar, velocity is the vector. For example, distance travelled is the scalar, displacement is the vector. Now in these instances, the vectors are the scalar values with the direction included in the answer. Now the easiest way to add a direction is to place a plus or a minus in front of the value. Now so this means that plus 20 meters per second and minus 20 meters per second vectors, because they include a direction now, show that the object is moving in different directions. So let's think about this. Scalars must be represented by a number value with a unit only, but vectors are represented by a number value with a unit and an arrow. The direction of the arrow shows the direction of the vector. The length of the arrow shows the size of the vector. Now adding two vectors is very simple. It's the standard addition you've carried out all the way through school. So if you had to add two scalars such as the volumes to each other, you would do volume 1 plus volume 2. So in this example, 10 plus 20 equals 30 centimeters cubed. But adding two vectors is more complicated because as well as the magnitude, you've also got to consider the direction. Now in physics, opposite directions are considered a negative. Now it doesn't matter which direction is considered the negative, only that one of them is. So for example, we could say up is positive and down is negative, or we could go vice versa depending on what the question states or what you decide. So we indicate directions of quantities in physics with plus or minuses. The only exception to the fact that vectors have to be pluses or minuses is temperature, because physics messed up this quantity when it first defined it. Now let's have a look at this example. In this case, the overall vector is 5 plus minus 2, so the answer is 3 newtons. So to find the overall vector, you must add the vectors if they're in the same direction, and you must subtract the vectors if they're in opposite directions. Now this overall vector is sometimes called the resultant vector, and the most common example of a resultant vector is a resultant force. Now a resultant force will cause an object to accelerate. If an object has no resultant force acting on it, it will not accelerate. It will stay at the same speed, which is what we call in physics inertia. Now this is actually the first principle of Newton's laws of motion. It's Newton's first law of motion. It's a fundamental rule of the universe. Now to add any two vectors which are not in the same plane, either the horizontal or negative as each other, you've got to draw a scale diagram. Now these diagrams accurately show the size and the direction of the overall vector, which we sometimes call the resultant vector. So here's an example of a scale diagram where we've added vector 1 and vector 2 to get the resultant vector. Now resultant in physics means the overall or the observed vector, and you can't just add them like you would do scalars. So the resultant vector is the straight line distance from the start of the diagram to the finish of the diagram. So to work this out, you firstly draw a scale diagram and you set your scale to your work. So for example, 1 square is 1 newton. You then draw the first vector with the correct correct length and direction. You then remember to always draw your arrowhead of your vector because that shows the direction it is acting in. You will then draw your second vector with the correct length and direction, and you place the tail of this vector at the head of the previous vector, which gives another name for a scale diagram, as is sometimes called a head to tail diagram. So here we've got our head and our tail of our two vectors next to each other. Then we draw our resultant vector in, as is from the tail of the first vector to the head of the second vector, as shown in this picture here. Now remember to always draw your arrowheads in for your vectors, as this shows the direction of the vectors. You then measure the length of the vector with the ruler and the angle with the protractor, and you convert this back with the scale to get your overall answers. Now remember, when you give an angle, you've got to say where the angle is measured from, either the vertical or the horizontal. Now in most cases in physics, you tend to find the vertical is the easier angle to measure from. So, to draw vectors, you've got to draw a scale diagram. These diagrams accurately show the size and the direction of the overall vector. So to draw your scale diagram, you've got to set a scale to your work, draw the first vector with the correct length and direction, draw the second vector with the correct length and direction. You place the tail of this vector at the head of the previous vector. The resultant vector is from the tail of vector 1 to the head of vector 2. You then measure the length of the vector with the ruler and the angle with the protractor, and remember to convert it with your scale back to your original values. Now, if you've got two vectors which are not at 90 degrees to each other, you can still add them via scale diagrams. However, we call these types of diagrams parallelograms of forces. So what you would do in this to work out the resultant vector is, the first step is you would draw in the same length vector as vector 1 with the same angle on the opposite side of vector 2 as shown in the diagram. Then you would draw the same length vector as vector 2 with the same angle on the opposite side of vector 1 as shown in the particular diagram. Then this is our parallelogram of forces because we've drawn a parallelogram. Now we then draw our resultant vector from the start of the vector to where the new lines meet up. So to measure the size of the resultant vector, you measure the vector with the ruler and convert it back to your value with a scale. You then find the direction of the resultant vector by measuring the angle with the protractor. The next topic we're going to look at are contact and non-contact forces, because there are many different examples of forces in the universe, such as the thrust force, the gravitational force, the tension, the magnetic force, the air resistance, the electrostatic force. Now a force is a push or a pull that acts on an object due to the interaction with another object. The unit of force is the Newton, and all forces are vector quantities, so they must be given with a magnitude and a direction. But the key word here is interaction, because forces can have a non-contact interaction. This means the objects do not have to be touching to exert a force on each other. Examples of this include the gravitational force and the electromagnetic force. So for example, the Earth and the Sun are not touching, yet there is still a gravitational force between them. This shows the gravitational force is non-contact. But some forces do need objects to be in contact with each other to exist, and we call these contact forces. So examples include friction, the reaction force, and tension. So the ball and the surface are rubbing against each other in this example. The bumps in each surface prevent a smooth movement, so this contact provides the frictional force. Here, in this example, the surfaces provide an upwards force on the ball to stop the ball falling through it and hitting the ground. So this contact provides the reaction force. In this particular example, the ball is pulling down on the cable. This causes the cable to stretch out. So this contact provides the tension or tensile force. So we can categorize all forces as either contact or non-contact forces. So examples of contact forces are friction, air resistance, tension, the normal force. So these occur when objects are physically touching, but forces can also be non-contact forces as well, such as the gravitational force, the magnetic force, the electrostatic force. So these are forces that can occur when objects are physically separated. So contact forces are forces that occur when objects are physically touching, which include friction, air resistance, tension, the normal force, whilst non-contact forces are forces that can occur when objects are physically separated, such as the gravitational force, the electrostatic force, and the magnetic force. Now, objects can exert non-contact forces in the universe by exerting a field into space. Now, a field is a region of space where a body can feel a non-contact force. So, for example, the Earth's gravitational field is a region of space where you can experience the Earth's gravitational force, which are represented by field lines. Now, the strength of a field is given by its field density. How many field lines are found in an area, or how close the field lines are to each other. So in a gravitational field, the closer you are to the object, the denser the field lines, the stronger the non-contact force. For example, in an electrical field, the closer you are to the object, the closer the field lines, the stronger the non-contact force. Now, interestingly, in an electrical field, the field lines always point in the direction a positive charge would take. So the field lines point outwards of a positively charged particle, but inwards to a negatively charged particle. And like we mentioned before, how close the field lines are tells you how strong this non-contact force is. So in a magnetic field, the magnetic force is strongest at the poles because that is where the field lines are the closest. The next topic we're going to look at is gravity. Now, mass is a measure of the matter found in an object. It's a scientific measure of how much particular matter is in an object. We measure mass in kilograms, so all values of mass should be given in kilograms. Mass is a scalar, which means it has no direction attached to it. The mass of an object remains unchanged in the universe, so mass is independent of any other factor in the universe. And to make this concept simpler, we assume all the mass of an object is found at the object's centre of mass. Now, weight is the force acting on mass due to gravity. Weight is caused by an object being in a gravitational field. Weight is a force which acts towards the centre of the Earth. The mass of the object helps determine how much weight an object experiences, but also the gravitational field strength determines how much weight an object experiences. Now, the force of gravity close to the Earth is due to the gravitational field around the Earth. So this tells us that both mass and gravitational field strength affect the weight. So the weight can change for an object depending on the gravitational field the object is in. Now, you tend to find the larger the planet or star, the larger the gravitational field, the larger the weight of the object. Now, weight is a force, which means it's a vector. Now, it always acts towards the centre of the gravitational field, which we tend to interpret on Earth as downwards, towards the centre of the Earth. And we measure weight in newtons. Now, weight and mass are directly proportional to each other because mass causes weight. So this means that when mass doubles, weight doubles. When mass halves, weight halves. They're directly proportional to each other. Now, we assume the weight acts from the centre of mass because that's where we assume all the mass of the object is. So mass is a measure of the matter in a substance. It's a scalar measured in kilograms. It's an unchanging value in the universe. Weight is the force of gravity acting on mass caused by the mass being in the gravitational field. It's a vector measured in newtons, and weight depends on gravitational field strength. Mass and weight are directly proportional to each other. Now, we can calculate weight with the equation weight in newtons is equal to mass in kilograms times by gravitational field strength in newtons per kilogram or meters per second squared. Now, you've got to remember the gravitational field strength of the Earth. It's actually 9.81 meters per second squared, which we simplify to 10 meters per second squared. This equation has to be memorized for your GCSE examinations. Now, note, we can symbolize the equation with weight W equals mg. Now, this g is the same g as the one found in the equation gravitational potential energy equals mgh. Now, this links because we know work done is equal to force times by distance. So work done is energy transferred. So the force is m times by g, and then times by the distance moved is mgh. So it works through like that. Now, the weight equation is very similar to another equation you cover in physics, which is F resultant force is equal to mass times by acceleration. And they're very similar because, in fact, they are the same equation, just written in different forms. They are the same physics principle, and it shows us that gravitational field strength is just acceleration, because gravity causes you to accelerate to the centre of the gravitational field. But the reason why you don't accelerate to the centre of the Earth is due to the reaction force, that contact force caused by the surface of the Earth. So let's just clarify what we've learned. Weight in newtons is equal to mass in kilograms times by gravitational field strength in newtons per kilogram or meters per second squared, and the strength of gravity on Earth is 9.81 meters per second squared. The next topic we're going to look at at is work done and energy transfer. Now, a resultant force can cause an object to accelerate in the direction of the resultant force, but a resultant force can cause energy to change between stores, which we call work done. Now, technically, a resultant force causes a change in energy store without the need for a wave such as light or sound. Now, work done is just another name for energy transfer between stores. Now, in many exam questions, they ask you to calculate the energy transferred and then the work done. Don't be tricked, it's the same value. It's just energy transferred and work done are two different names for the same effect. Now, work can be done on an object if the object is displaced, moved, in the direction of a resultant force. So if an object does not move in the direction of a resultant force, no work is done. Now, we can calculate the work done with the equation work done in joules is equal to the force in newtons times by the distance moved in the direction of the force, the displacement in the direction of the force. Now, we can actually use this to define what 1 joule is. Now, 1 joule of energy is the work done needed to move 1 newton of weight or force by 1 meter in the direction of force. So work done equals force times by distance, so 1 joule is equal to 1 newton times by 1 meter. So in this particular example, what's the work done due to gravity? Now, let's have a look. What's the displacement in the direction of gravity, which is going to be downwards towards the center of the earth? It's 2 meters. What's the force? Well, we know the mass is 10 kilograms, so the force must be the weight, so we do 10 times by 9.81. That's our force. We times that by our displacement in the direction of the force, 2 meters. So it is then 196 joules. And this is the work done due to the gravitational force, which could only happen when the object's moving vertically, as that's the direction that gravity and the gravitational force acts in. Now, what happens in this particular example? Well, the work done is going to be 0 due to gravity. That's because gravity will act in the vertical plane, but in this instance, the object is moving in the horizontal plane. So whilst it's moving 4 meters, it's not moving 4 meters in the direction of the resultant force. So when we do our calculation, we can work out our force in the same method, 10 times by 9.81, but then we're going to multiply it by 0 because the distance moved vertically, the direction of the force, is 0. So there is a work done in this example, but it's not done due to gravity, it's done due to a horizontal force because that's the direction it is moving in. Now, a common example of where work is done in the direction of a force is a particle accelerator. Now, in a particle accelerator, there are 2 forces found in the accelerator, the magnetic force and the electrical force. Now, in this diagram, you'll notice in the particle accelerator, the only force doing any work in making the particles change speed and accelerate in this instance is the electrical force, as it's in the direction of the movement. The magnetic force, which doesn't make particles do work in this instance, as it's not in the direction of the movement. So the particles are not moving in the direction of the magnetic force, it's only there to deflect the particles, so the magnetic force does not do any work onto the particles. So let's just clarify what we've learned. When a resultant force causes an object to move through a distance, work is done on the object. A resultant force does work on an object when the force causes a displacement of that object. So work done in joules is equal to the resultant force in newtons times by the distance moved in the direction of the force in meters. 1 joule of work is done when a force of 1 newton causes a displacement of 1 meter. But always remember, when work is done against friction, this will cause the energy to be transferred to the internal energy of the surroundings. So in this instance, friction can act as a resultant force, which makes the energy change stores in the process. The last topic we're going to look at in today's revision session is forces and elasticity. Now, we've previously looked at what resultant forces can do. They can cause an acceleration. They can cause energy to change between stores. They can cause work to be done. Now, interestingly, by the way, work can also be done when charge flows in an electrical circuit. But in this final part of the revision session, we're going to look at the third effect of resultant forces. These resultant forces can cause material deformation. So the first type of deformation is when an object increases in size due to a force placed on it. Now, a force which causes extension is called the tensile or tension force. So if you apply tension to an object, the object will increase in size. But it's always got to be a resultant force that does this, so there's got to be more than one force acting on the object. An object can decrease in size due to a force placed on it, and this is called compression, and it's caused by a compressive force. So when a compressive force is applied, the object will get smaller in size. But once again, it's a resultant force, so more more than one force has to be applied on the object. Now, an object does not have to change overall size, but can change shape if a resultant force is placed upon it, and we call that distortion. So once again, more than one force has to be applied onto the object because it's a resultant force. But now, there are two ways an object can behave if you've got material deformation being produced by a resultant force. It can act either elastically or inelastically. An object is elastic if the object regains its original shape after the forces deforming it are removed. So when the deforming force is removed from an elastic object, it will return to its original shape. An object is inelastic if the object does not return to its original shape if the deforming forces acting on it are removed. So when the deforming force is removed, the object does not return to its original shape, it stays deformed. Now, another name some people give to inelastic objects is plastic, but you've got to be careful about this, because the common term plastic in the everyday sense means like plastic bottle, plastic bag is the chemistry definition of plastic, and it means a polymer. Now, in physics, other objects can be plastic as well as polymers. Now, many objects have an elastic and inelastic region depending on the size of the deforming force placed upon it. Now, at lower deforming forces, the object acts as elastically, but at higher deforming forces, it will act as an inelastic. So, an object is elastic if the object regains its original shape after the deforming forces acting on it are removed. An object is inelastic if an object does not return to its original shape if the deforming forces acting on it are removed. Many objects are elastic at certain deforming forces, but inelastic at larger deforming forces. Now, Robert Hooke was a scientist who examined elastic materials by placing a deforming force on them, and he realized the following: the more the deforming force placed on a material, the more it extended. That with some materials, they were in a directly proportional relationship, so if the deforming force doubled, the extension doubled, and with a large enough deforming force, the material will snap. So just remember, a deforming force can cause an extension. Now, the extension is measured as the difference in length between the length with a deforming force and the length without the deforming force. So extension is the change in length of the material, or delta L. So it is the length with a deforming force minus the length with no deforming force. So just remember, the greater the deforming force, the greater the extension of the object, which is also true for compression, just in the other direction. Now, Hooke worked out the following: that the extension and the deforming force increase at the same rate. They are in direct proportion. As one doubles, the other doubles. This is Hooke's law. And when Hooke plotted this relationship, he achieved a straight line trend in his graph, which is the elastic phase of an object. So an object is in its elastic phase when the object is a straight line. Now, the straight line section shows a force and extension are directly proportional, because when you get a line of best fit, which is a straight line through the origin, they are directly proportional to each other. So if the force extension graph of a material is a straight line, the object is elastic, the object obeys Hooke's law. Now, the graph must go through the origin, as when the deforming force is 0, the extension is 0, because the deforming force causes an acceleration. If a student does not plot it through the origin, they've measured length and not extension, which is a common mistake made in examinations. Now, Hooke realised that if there was a large enough deforming force placed on the material, that force and extension are no longer directly proportional. So at this point, we say it's the limit of proportionality. It's the limit of where it's a straight line. After the limit of proportionality, the material acts as an inelastic. Eventually, if enough deforming force is placed on the material, the object will snap, which is called the breaking point. So we can actually use this particular graph to work out some values. The gradient of the force extension graph is called the spring constant. Now, this graph places the force exerted on the object on the y-axis. It places the extension caused by the deforming force on the x-axis. Now, the force should cause extension, which means the line should go through the origin. Remember, if it doesn't, the experiment has not measured extension, they've measured length. Now again, if it's a straight line, it must be in the elastic phase, and the spring constant, which is the gradient of our line, is the amount of force needed to extend the object by 1 meter. It is how stiff an object is. The stiffer an object, the larger the spring constant. The stiffer the object, the more difficult it is to extend. Now the spring constant, because it's a constant, can only be taken on the straight line section of the graph, because at that point the gradient is constant, so your spring constant is constant. Now, to take your gradient, you've got to draw a right angle triangle on the graph with a line of best fit providing the hypotenuse. Then make your gradient triangle as large as possible, as it increases the validity of your results as you're considering more values. You then work out your gradient by doing the change in y over the change in x, or the change in force over the change in extension, or F over E, and our gradient is our spring constant. And this allows us to work out the units of the spring constant because we're doing force divided by extension, so it's newtons over meters. So the unit of the spring constant is newtons per meter, and that's how we can work out that particular value. So the spring constant is the proportionality constant between the deformant force and the extension that force causes. So this means for a material obeying Hooke's law, the deformant force in newtons is equal to the spring constant in newtons per meter times by extension in meters, or in simple form, F equals KE. Now remember, this equation needs to be memorised for your examination. It is not given to you on your equation sheet, but this law is only true for elastic objects, not for inelastic objects. Now when this deformant force occurs, this allows work to be done on the material, like we mentioned before. So this allows energies to be stored as elastic potential energy in the object. So a force that stretches or compresses a spring does work, and elastic potential energy is stored in the spring, provided the spring is not inelastically deformed. The work done on the spring and the elastic potential energy store are equal. Now you can work out the energy stored in an elastic object from the elastic potential energy equation learnt in paper 1, which is elastic potential energy store is equal to a half times by spring constant times by extension squared. But that equation does not need to be memorized for your examination. It is given to you on your examination sheet. Now here's an example of a question with Hooke's law. A spring has a spring constant of 25 newtons per meter. How much force is needed to make the spring extend by 0.10 meters? Well, force equals spring constant times by extension. 25 times by 0.10, it's 2.5 newtons. So let's just clarify what we've learned. Hooke's law states that the extension of a spring is directly proportional to the force applied, provided its limit of proportionality is not exceeded. The deformant force in newtons is equal to spring constant in newtons per meter times by extension in meters. The spring constant is the force needed to extend the spring by 1 meter, assume its length of proportionality is not reached. The larger the spring constant, the stiffer the spring. Now the gradient of the line when the line is straight is the spring constant, and it must go through the origin, otherwise the extension is not being measured. Now when it is a straight line, it's elastic, it's obeying Hooke's law. When it is a curving line, it is inelastic, it doesn't obey Hooke's law, and we can only take the spring constant from the straight line section of the graph. So when an object obeys Hooke's law, it is elastic and an elastic potential energy store. When an object does not obey Hooke's law, it is inelastic and it is not an elastic potential energy store. When it's a straight line through the origin, that shows us that it's obeying Hooke's law and that force and extension are directly proportional to each other. When the point where the line starts to curve is where it acts inelastically and is called the limit of proportionality, because there is no more direct proportionality shown beyond that point. So you've got the elastic region, the inelastic region, and then the breaking point. Once the material passes its limit of proportionality, it's inelastic and will stay deformed once that force is removed. So to summarize, what have we learned? Scalar quantities have a magnitude only. Vector quantities have a magnitude and an associated direction. A vector quantity may be represented by an arrow. The length of the arrow represents the magnitude, and the direction of the arrow, the direction of the vector. A force is a push or pull that acts on an object due to the interaction with another object. All forces between objects are either contact forces, forces that objects when they're physically touching, or non-contact forces, objects when they're physically separated. Force is a vector quantity, and you should be able to describe the interaction between pairs of objects which produce a force on each other, and the forces are represented as vectors. Weight is the force acting on an object due to gravity. The force of gravity close to the Earth is due to the gravitational field around the Earth. The weight of an object depends on the gravitational field strength at the point where the object is. Weight is equal to mass times by gravitational field strength, and the weight of an object may be considered to act at a single point, referred to as the centre of mass. The weight of an object and the mass of the object are directly proportional, and the weight is measured using a calibrated spring balance called a Newton meter. When a force causes an object to move through a distance, work is done on the object, so a force does work on an object when the force causes the displacement of the object. The work done can be calculated with the equation work done times by force times by distance moved along the line of action of the force. 1 joule of work is done when the force of 1 Newton causes a displacement of 1 metre. So 1 joule is equal to 1 Newton metre, and you should be able to describe the energy transfers involved when work is done and convert between Newton meters and joules. And remember that work done against frictional forces causes an object to rise in temperature. Now you should be able to give examples involving stretching, bending and compressing of an object, explain why to change the shape of an object by stretching, bending or compressing more than one force has to be applied, and describe the difference between elastic deformation and inelastic deformation caused by stretching forces, and the extension of an object such as a spring is directly proportional to the force applied to it provided the limit of proportionality is not exceeded. So F equals KE, and this applies to compression as well as extension. A force that stretches or compresses a spring does work, and the elastic potential energy is stored in the spring provided the spring is not inelastically deformed. The work done on the spring and the elastic potential energy stored are equal. So you should be able to describe the difference between linear and non-linear relationships between force and extension, calculate the spring constant in linear cases when it's a straight line, and then calculate the work done on the elastic potential energy stored with the equation 1/2 times by spring constant times by extension squared. I hope you've enjoyed this revision session on the interaction of forces found in GCSE Combined Science Physics, and have a lovely day.